You can start now.
Okay, cool. So today we'll be talking about multiplicative orders, which is a topic in number theory. And getting straight to the point, given a prime p in a non-zero residue A, it's like a non-zero number, the order of A mod p is defined as the least positive integer k, for which A to the k is congruent to 1 mod p. And like this is the definition, so k is the order. And then just for syntax, we write this as order subscript p of A, so order mod p of A. And the first thing like you should probably think about is, okay, does this always exist? And yes, it does, because Fermat's little theorem tells us that A to the p minus 1 is congruent to 1 mod p. So the order will always be not more than p minus 1. And let's see why this idea of order is useful. So this first proposition is like the most useful thing about orders. And it says that if we have an integer n such that A to the n is congruent to 1 mod p, then order mod p of A divides n. And let's see why that is. So we'll proceed by a proof by contradiction. And our strategy will be to try to construct a smaller exponent y such that A to the y is congruent to 1 mod p, since this would contradict the minimality of the order. Since if you'll recall, we defined order as the smallest exponent such that this is congruent to 1. So we'll do this by using Bayes' theorem. And first note that the GCD of the order mod p of A and n is less than, or if we let this be R, then we know that R is less than the order mod p of A. And this is because of our assumption that order mod p of A does not divide n. Because if it was equal to order mod p of A, then that would mean that order mod p of A has to divide n. So now we can cite Bayes' theorem, and that says that there exists integers x and y such that x times order mod p of A plus y times n equals to r. Bayes' theorem just says that if you have, let's say, GCD, let's see, it's weird. If you have GCD of a comma b equals to, let's say, like c, then there exists integers x, y such that x times a plus y times b equals to c. So we're applying that straight from this GCD statement. And then now let's look at what a to the power of r mod p is. Just plugging in our definition from Bayes', we get this is equal to a to the x times order of p, order mod p of a plus y times n. We can split that up into a to the power of x times order mod p of a times a to the power of y times n. And then this becomes a to the power of order mod p of a to the power of x times a to the power of n to the power of y. And this is all mod p. So now we note that this term looks familiar. We defined order mod p of a as the smallest number such that a to the power of the order is congruent to 1. So this is congruent to 1 to the power of something. And then also we said inside our problem statement that we have a to the n is congruent to 1 mod p. So this is also congruent to 1. And that means that this whole thing, a to the r, is congruent to 1 mod p. But now the contradiction is that, as we said earlier, r is less than order mod p of a. So we've constructed a exponent that's smaller than the order, but still has that a to the exponent is congruent to 1 mod p. And that's a contradiction. So our assumption is wrong, and that means that order mod p of a divides n. And we'll quickly see like that a lot of problems involving order use this proposition. And also as a quick corollary of this proposition, we have that order mod p of a always divides p minus 1, because we always have, by Fermat's little theorem, that a to the p minus 1 is congruent to 1 mod p. And then this, since that if you plug in p minus 1 as n over here, this tells us that order mod p of a divides p minus 1. So let's see a quick example of why this is useful. And this is example 1.1. Show that for all primes p congruent to 2 mod 3, A is congruent to B mod P if and only if A cubed is congruent to B cubed mod P. So one direction of this is obvious. It's pretty obvious that if A is congruent to B mod P, then we have A cubed congruent to B cubed mod P. And the interesting direction is the other direction. So from this statement, we want to prove this. And let me write that over here. So given A cubed congruent to B cubed mod P, where P is congruent to 2 mod 3, prove that A is congruent to B mod P. So our first step will be to deal with the edge case where both are 0. If A is congruent to 0, then obviously from this equation we have that B is congruent to 0 mod P, so A is congruent to B mod P. And that's kind of boring. So now we can assume that A and B are not 0 mod P or not congruent to 0 mod P. And what this lets us do is we can multiply by the inverse of B. Specifically, we will multiply by the inverse cubed. So this gives us A cubed times B inverse cubed is congruent to B cubed times B inverse cubed. And this inverse always exists because it's mod of prime. And everything that's not 0 is relatively prime to, or not congruent to 0, is relatively prime to that prime. And by definition of inverse, this right-hand side just becomes 0, since it's B times B negative 1 cubed, or not 0, it becomes 1. So we have A times B inverse cubed is congruent to 1 mod P. And now we have something of the form something to the power of something is congruent to 1 mod P. So it's a good time to break out orders. Okay, we can just use the notation for now. I usually let D be the order, just like save writing. But I guess the first time through, it's probably good to write it all out. So we write our equations given by the proposition. Since like if we have something to the power of something is congruent to 1, then we know order divides that exponent. So order mod P of A b to negative 1 divides 3. This is from this equation, since we have that this to the power of 3 is congruent to 1. And then also by Fermat's little theorem, or the corollary from earlier, we have that the order divides P minus 1. And you know that when some number divides two other numbers, it divides their GCD. So this gives us order mod P of A to the A times B inverse divides GCD of 3 and P minus 1. But now this is where this extra condition, P is congruent to 2 mod 3 comes in. So since P is congruent to 2 mod 3, this means that P minus 1 is congruent to 1 mod 3. So in particular, P minus 1 and 3 are relatively prime, since this isn't 0, and if it's not 0, then it's relatively prime, since 3 is also prime. So this tells us actually that order mod P of A times B inverse divides 1, and that means that it can only be 1, since 1 is the only factor of 1. And now we use the definition of order. So this tells us that AB inverse to the power of 1 is congruent to 1 mod P. And that just finishes. Since we now have, if we multiply both sides by B, A is congruent to B mod P. Okay, were there any questions on that example? Okay, cool. We'll be seeing a lot of the same techniques inside later examples. So the next example will use that, and also a pretty famous trick called the smallest prime trick, which shows up in a lot of problems, especially involving order. And it is find all positive integers n such that n divides 2 to the n minus 1. And this is like a pretty classic problem to do when learning orders. So positive integers n such that n divides 2 to the n minus 1. And so this tells us that 2 to the n is congruent to 1 mod n, but we kind of don't want to work with composite numbers because composite numbers are not nice. So let's just take some prime dividing n. we might choose extra conditions on this prime later, but for now, let's just say it's any prime. So this also gives us, since p divides n, it also divides 2 to the n minus 1. So we can say that 2 to the n minus 1 is congruent to 0 mod p. And this gives us 2 to the n is congruent to 1 mod p. So this looks like our nice order equation again. So let's let d equals to the order mod p of 2. This equation from here gives us that d divides n. And from our Fermat's theorem, we have d divides p minus 1. So there's no immediate problem with this yet, but here's where the smallest prime shift comes in. Oh, this is question 1.2. Find all positive integers n such that n divides 2 to the n minus 1. I wrote it over here. Oh yeah, I guess as a start, we can note that n equals 1 obviously satisfies this since 1 divides 1. And then I claim that there are no other solutions. So yeah, now the smallest prime shift. So remember that we just chose some random prime p dividing n. We can actually be more specific. Let's choose the smallest prime dividing n. And n being greater than 1 here is actually pretty important, since that ensures that it will have a smallest prime divisor. So now, looking back on these equations, there might be a problem. And in particular, let's write out d divides GCD of n and p minus 1. So since we said that p is already the smallest prime dividing n, it's like the smallest factor of n. But p minus 1 is smaller than p. So if this GCD were to be more than 1, that would mean that there's something dividing p minus 1 and something dividing n. So we would have an even smaller factor of n, which is impossible. And that means that this GCD must be 1. So we once again have the order is 1, or 2 to the 1 is congruent to 1 mod p. And this tells us that 1 is congruent to 0 mod p. So p divides 1, which is impossible. And thus we have our contradiction. So there's no solutions where n is greater than 1. And thus n equals 1 was our only solution. Any questions on n divides 2 to the n minus 1? Also, let me know if we're going a bit fast, since we should have more than enough time for the last example I've planned. Okay. Before we get to our next example, there's a bit more theory to know. So about primitive roots, a residue G is called a primitive root modulo P if the order of G mod P is P minus 1. So like the largest possible, says that P minus 1 is the largest possible order. And this is useful because we can actually guarantee that a lot of G's exist for each prime. In fact, there's phi of P minus 1 G's for each prime, but usually you won't need that many, you'll just need 1. And let's look at MA's first nice number theory problem in a really long time. So this is this year's AME 1 problem 14. And for any positive integer A, sigma of A denotes the sum of the positive integer divisors of A. Let n be the least positive integer such that sigma of A to the n minus 1 is divisible by 2021 for all positive integers A. Find the sum of the prime factors in the prime factorization of n. Okay, so first thing, looking at this problem, it's inherently a two-part problem. So our goal is to show that if n satisfies some condition, then it will satisfy this problem statement. And then we want to find the smallest possible n with that condition. And also that the problem statement forces n to satisfy that condition. So I guess this will become more clear once we start solving. Okay, so let's see what this condition about sigma of A to the n minus 1 divisible by 2021 actually means. First thing, it's pretty important to know the formula for sigma of n, like some of the factors of some number. And if we have a equals to, like, let's say prime 1 to the power of, I don't know, e1 times prime 2 to the power of e2, all the way to prime k to the power of e sub k, then sigma of a, the sum of the factors, is 1 plus p1 squared plus all the way to p1 to the e1 times 1 plus p2 squared all the way to p2 to the e2, and so on, all the way to 1 plus pk squared plus all the way to pk to the e sub k. And the reason for this is that this, like, I guess if you expand this out, this gives you all of the factors, since you choose one prime power of p1, one prime power of p2, and so on. And in particular, this will turn out pretty nice for this problem. So if we use the geometric series formula to figure out, wait, actually, give me a sec. Yeah, okay, sigma of a to the power of n minus 1. So if we take a to the n instead, then we have, like, keeping this, then it's p1 to the e1n times p2 to the e2n all the way to p sub k to the e sub kn. And this is like not, the n is not subscript, it's just multiplied. So now our sigma of a, like sigma of a to the power of n, becomes, using the geometric series formula on this, it becomes p1 to the e sub 1n plus 1 minus 1 over p sub 1 minus 1 times p sub 2 to the e sub 2n plus 1's in the exponent minus 1 over p sub 2 minus 1, and so on, all the way to p sub n to the e sub n plus 1 minus 1 over p sub n, or k here, p sub k minus 1. And we're given that this should be 1 mod 2021. Yeah. Or this has to be 1 mod 2021 for any a that we choose. So this looks pretty nasty, but there's actually something we can do here. Since we have a lot of freedom, since we can choose a to be whatever, and this condition still has to be true. So in fact, let's just choose a to be p sub 1 to the e sub 1. And then this gives us now that just p sub 1 to the e sub 1n plus 1 minus 1 over p sub 1 minus 1. This is, let's call this a prime. So sigma of a prime to the power a prime to the n equals this. This also has to be 1 mod 2021. And same for all of these other factors. So in fact, we actually have a stronger thing. We need that for every prime power, this thing is congruent to 1 mod 2021. And if that is true, then it will actually prove the general case, since we have a bunch of ones now that multiply to 1 mod 2021. So if it is true that, or if we can find n such that it is true that each of these is always congruent to 1, then it will be true whenever we have like a product of prime powers as a as well. So what this tells us is that we only need to care about the case where a is a single prime power. And let's try to figure out n for which this is always true. So now notice that we have a p1 minus 1 in the denominator. This is annoying because dividing by 0 errors. So we have to do casework based on p mod. Okay, also another trick is that we note that 2021 is not prime. It's in fact 43 times 47. So we want to just split it into its prime factors. This is p to the en plus 1, or it's equivalent to this, divided by this is congruent to 1 mod 43, and it's congruent to 1 mod 47. So these both have to be true. And in fact, the work for these two cases turns out to be pretty much identical, except it's just 47 instead of 43. So let's focus on solving this first. And as I said before, p minus 1 in denominator is annoying. So let's deal with that case. Let's say we have p is congruent to 1 mod 43. Well, then remember that sigma of a, inside this case, sigma of a to the n, is equal to 1 plus p plus all the way to p to the en. And we want to show that, or we need that this is congruent to 1 mod 43. But in fact, since p is congruent to 1, we can just plug in 1 everywhere here. So this is congruent to 1 plus 1 squared plus all the way to 1 to the en. And then inside this list, we have a single 1 here, and then we have en 1s here. So this is congruent to en plus 1, and we need that this is congruent to 1 mod 43 for every e. So in particular, this says en is congruent to 0 mod 43. And we need this for every e. So just choosing e equals 1, we get n is congruent to 0 mod 43. And it turns out this is also sufficient, since if 43 divides n, then this will, or en will always be congruent to 0 mod 43. So this case tells us that we must have 43 divides n. And in our case 2, we don't have divide by 0 problems. So we take this expression, and then we can multiply both sides here by p minus 1, since it's not 0, and we're modulo prime, so division works fine normally. And we get p to the en plus 1 minus 1 is congruent to p minus 1. And just getting rid of the 1s, we get p to the en is p to the en plus 1 is congruent to p mod 43. And here we would like to divide by p, but we have to deal with the other annoying case where if p is congruent to 0 mod 43, it's a lot easier in this case, since remember that we need to prove that 1 plus p plus all the way to p to the en is congruent to 1 mod 43, or you need to find what n satisfy this. And if p is congruent to 0 mod 43, then this is just really easy, since these all become zeros. So we just need, or the condition 1 is congruent to 1 mod 43 is true for any n. So this case does not bother us, and we can divide by p now. So p to the en is congruent to 1 mod 43. So finally, after all of that busy work, we've gotten to the orders part of the problem. Let's let d equals to order mod p of 43. This equation tells us that d divides en, and Fermat's little theorem tells us that d divides 42. And it looks like we're stuck because this doesn't really tell us anything about n immediately. D can still be quite a few number of values, since 42 has like 2 times 3 times 7, so 8 factors. But here is, remember I mentioned primitive roots, and we can still choose p to be, or we can choose p to be whatever we want it to be. So in fact, let's choose p that is congruent to a generator or a primitive root mod 43. And the reason why we can do this is that, well, 1, probably like 2 or something is a primitive root, but 2, Dirichlet tells us that if we have like some zero, or we can always find a prime that's congruent to something mod something, as long as they're relatively prime. Like if we have a condition x is congruent to a mod b, where GCD of a and b is 1, we can actually find infinitely many primes for x that satisfy this. So let's just choose a prime p that's a primitive root mod 43. And what this tells us now is that the order, this is backwards. Oops, this is order mod 43 of p. So this tells us now that the order mod 43 of p equals to 42, since by definition the primitive root is just the prime minus 1. And now this gives us a lot more information, since we now plug this into here, and we get directly 42 divides en. And remember, we can also choose e to be whatever we want. So we just let e equals 1, and this gives us 42 divides n. And in particular, if n satisfies this, this is always true. So this case has given us that we need 42 divides n, and 43 divides n. And since the 47 case should work symmetrically, we can assume that it gives us 46 divides n and 47 divides n. So if we return to the problem statement, it wanted us to find, let's see. Okay, it exists somewhere. Oh, there it is. We want to find the sum of the prime factors in the smallest possible n. And the smallest possible n should just be the LCM of all these things that must divide it. So we take LCM of 42, 43, 46, and 47. This should be 2 times 3 times 7 times 43 times 23 times 47. And want the sum of all of the prime factors. So 2 plus 3 plus 7 plus 43 plus 23 plus 47. Arithmetic 113, 120 equals 125. And that should be our answer. Okay, any questions on this last problem? I guess to summarize what we did inside this problem, it was just or figure out what this condition means by applying the formula, and then realize that it looks pretty close to an order thing. If we, the second step was split it into just the primes case, because you have a lot of freedom with A. So you can just first check out what happens if you plug in just the prime power, and then realize that that's equivalent to solving the whole problem. And then after we have the prime power thing, which is here, we realize that this is very close to orders, but it has a few problems in which when the denominator is 0, or we have p is congruent to 0. So we dealt with those. And then we finally got it to this nice condition here with p to the something is congruent to 1 mod 43. And we tried applying orders, but realized it wasn't strong enough. But we realized we could choose a primitive root for p. And then that gave us enough power to be able to derive a condition on n. And in general, with orders, they'll be seeing this a lot, where you get to something to the power of something is congruent to 1 mod a prime, and then you'll let the order, and you'll write down the two divisions, one from Fermat's theorem, one from just the equation that you got to. And usually you'll either have to choose some special prime from the modulus or some special residue in order for the orders to give you some information that you actually can use. All right, that's my lecture. There's some really nice problems at the end that you guys can try. And yeah, are there any last questions? Okay, I'll let